Okay, so here's the second day of electricity, and this is when it's going to get a little more interesting. First of all, measuring voltage. If we're going to measure voltage, we usually use this thing here. It's called a multimeter. It's an instrument to measure volts, amps, and ohms, and we're going to actually do it with physical things. So we're going to kind of cruise through these because you know I don't know if you'll remember this stuff, but we'll get it better when we do it by hand. So if you look at this, it does say when you measure voltage, it's the easiest because you just stick one of these probes on one side, one of these probes on the other, and you can see how much voltage drops from one side to the other side of a resistor. Remember, resistors are like rocks in a pipe, and it's slowing stuff down, so you want to see how much pressure drops off after it crosses, over the rocks. Because voltage is like pressure. Okay. So yeah, I showed you one of those. You can measure current too. This is not the right way. You got to remove. The weird thing with current is you got to take out one of the wires, and then you use the multimeter to connect it. So the flow has to go through the multimeter. And you'll see here you set it for voltage or current, or down here, here's ohms. Resistance, you have to turn off the battery so you don't have all the voltage going through there or current. Here's the important part. This is it. So we cruise through those other ones. You don't really have to, do the section here. Oh, we can write them in. So we can set it to the proper amp range. DC or AC. Current flow must go through the meter, or you fry it. So when you do the multimeter for resistance, you're going to do the proper ohm range, and you're going to measure the resistor, or what was that one? You're going to measure the. Oh well. Anyway, power must be off when you do the resistors. Here's the important part. This is it. Put a big star next to this because this is Ohm's law. Ohm's law explains the mathematical relationship between current, voltage, and resistance. So this is basically all the good stuff, all our math problems. So mathematical relationship between current, voltage, and resistance. So there's 3 different ways to do it, but my favorite way is to make the triangle. I'm sure in physics class or science class you've done this with density, mass, and volume. So you kind of make this triangle, V, I, R, and you can come up with all 3 of these equations. Remember, current is measured in amps, but the symbol for it, I don't know if you know that, but the symbol for it is I. I for current. I looked it up, and it's actually because of a French word dealing with current, is why it's an I. I always wondered why that was, why it wasn't an A for amps. Voltage is V and R for resistance, right? So when you see these formulas, there's 3 of them, but they're all just solving this equation in a different way. Like if I wanted to solve for R, I'd divide by I, right? And then you'd have this equation. If I want to solve this equation for V, I multiply by R. So you can jump between them. A quick way is to do this, because if I want voltage, I cover it up with my thumb, and voltage is I times R. See how they're next to each other? Just like this one. If I want resistance, I cover up the R, and look, it's V over I. Right? And if I want current, which is I, you cover up the I, and you get V over R. So you see how you can just draw this one triangle and find all 3 equations. So you could do easy kind of questions like this. And we'll look at this real quick just to make sure, because Ohm's law, like I said, is the most important thing. Every math problem you do in here will use Ohm's law. Some of them get tricky, but the basics are really not hard. Voltage is V, current is I, resistance is R, but the units are volts, amps, and ohms. Okay, so, and this is what I was just showing you, which is kind of cool. All right, so here's an example. All right, so let's do an example here of an Ohm's law question where you get to use these formulas. So it says a flashlight uses a 6-volt battery, so I'm going to circle that, and has a bulb with resistance of 150 ohms. How much current will be drawn? So the question is how much current. And if I remember, current is I. So I'm going to write my equation. Remember, just like our machines problems, we write our equation. So I cover up the I, and I wrote V over R. So if I have my volts, which is 6, and my resistance, which is 150 ohms, and I divide that on my calculator, 6 divided by 150 is 0.04 amps. That is the correct answer. It's weird to write a decimal one in engineering. Usually what you'll see us do is transfer them over. So I can swing it over a couple decimal places. Usually in engineering we move things by threes. So I'm going to move it over 3 decimal places and you get 40 milliamps. But we'll go into that more in the future. But just know in my formulas I got to use amps and stuff. But and for end answers we usually make them a little prettier. Okay. So circuits. Let's see. We're going to attack these circuits here. Okay, so if you look at this, there's basically 2 different ways components can be connected in a circuit. And sometimes you can have a combo of the both, but really you have a choice of 2. There's series circuits where components are connected end to end, like if this was a battery and that was a resistor and this was a resistor. And there's only one path for it to go through. These could be batteries or capacitors or resistors. But see how the electricity only has one path to go? And then these are called parallel circuits where you can have multiple paths for the current to flow. So we can go down this path, you can go right past this guy and go up here. So electricity could kind of flow a bunch of different ways. It doesn't have to just go one path. Like I could just go woo, right here with an electron. Or you go over here. Really, it's a flow of electrons. It's not like a single electron's moving. Anyway, so that's the difference between the 2. So make sure you know that. So we have series. They're connected end to end, and there's only a single path for current to flow. In parallel, there are multiple paths for current to flow. Okay, and this is Kirchhoff's laws, and basically these are going to help you solve problems too. So you have Ohm's law, which is the VIR thing, and you have Kirchhoff's laws, which says the sum of the voltage drops in a series circuit is equal to, or equals, the total applied voltage. That means if you have the little, you can add up all the individual voltage drops around it, and it equals the total volts of the battery. And then Kirchhoff has a current law too. The total current in a parallel circuit equals the sum of the individual branch circuits. So it's kind of like here, the voltage will be the same the whole time. Just like in here, the current's the same whole time, and it breaks up the voltage into parts. Well, here the voltage is the same the entire time, and it breaks up the current into parts. So the current added up over the little parts equals the total current. So those are handy laws, and we'll use them in some problems here. So let's jump back to this real quick. A series circuit is a circuit that contains only one path. We're going to hammer that home for current to flow. If the path is open anywhere, then the current stops flowing to all components. So if you broke, this wire anywhere, then there's no more current going on at all. So, yeah. And then here's another breakdown of series circuits, because we're going to start with series first. It's easier because the current only flows one way. So what's kind of nice about this is if you want to know the total resistance, you can just add up the resistance of resistor 1, resistor 2, and resistor 3, and you get your total resistance. And if you want to know your total voltage, it's 12, but the voltage of drop over this resistor plus the voltage drop here plus the voltage drop here will always equal 12. So that's kind of nice. So current flowing through every series component is equal. So we're going to jump back to our notes here. And that's an important thing. In a series circuit, current is always the same. The total resistance is equal to the sum of all the resistances, and the sum of all voltage is equal to the total applied voltage. And that's called Kirchhoff's voltage law. We kind of saw that on the other side. Kirchhoff voltage law. Okay, so let's look at an example of a series circuit. So let's jump over here and we'll kind of do one together. So for this series circuit, we want to find the total resistance. We want to find the current flowing through each spot. We want to find the voltage across each spot. And we want to verify Kirchhoff's voltage law. So what's cool is it's really easy for some of these. The total resistance is just to take each piece added up. So if I want to know total, I'll write this. Watch this. VT. See how I put a little t there for total? VT is going to equal the V at resistor 1 plus the V at resistor. Oh, wait. Let's shoot. Gosh darn it. I'm doing total resistance. So RT equals the resistance of resistor 1 plus the resistance of resistor 2 plus the resistance of resistor 3. Holy cow. All I got to do is add them? Heck yeah. It's a nice start. So I'm going to take 220 ohms plus 470 ohms plus 1.2 kiloohms. Remember, kilo means 1,000. So it's really 1,200 ohms. You got to move that decimal place over 3. 1, 2, 3. So it's 1,200 ohms. If I add all those up, 220 plus 470 plus 1,200 equals a grand total of 1,890 ohms. Now it's typical in here, not in engineering, not to leave an answer bigger than 1,000, really bigger than 999. So I'm going to move the decimal place back 3, and I'm going to say it's 1.89 kiloohms. Okay, kind of like this one here, right? You don't want a ridiculously big number. Okay, engineers love the numbers between 1 and 1,000. Okay, so that's my total resistance. Now I'm supposed to find the total current. Well, guess what? The total current, we're going to use Ohm's law. Okay, what's Ohm's law again? Well, let's look at our triangle. Boom, right? We're going to look at our triangle, VIR, and we're going to do, we're looking for current, so I cover it up, and I'm going to say, okay, total current, IT, equals VT, total voltage, over total resistance, RT. Okay, so do I know my total voltage? Heck yeah, you do. It's right there, 12 volts. 12V over, do I know my total resistance? Yep, I just found it out. Now don't use the kiloohms, use regular ohms. That's why I wrote it down, 1890 ohms. So if I take 12 volts divided by 1890 ohms, I get 0.006. I'm going to write it off to the side, 0.00634 amps. That's my current. And then, remember, we don't like really tiny numbers either, so I'm going to have to move my decimal 3 places and say 6.34 milliamps. Okay, is my answer. I still like this answer, and if I use it in the future, I got to use that. Oop,